Welcome to the People of AI podcast, showcasing inspiring people with interesting stories in the field of artificial intelligence. I'm Ashley Oldacre. Let's jump right in. This podcast is sponsored by Google. Any remarks made by the speakers are their own and are not endorsed by Google. Hi, everyone. Welcome. I'm joined by my wonderful co-host, Gus. Gus, I'm super excited because we have a wonderful guest today.
Hi, everyone. Glad to be here.
I'm delighted and honored to welcome a legend in the field, François Chollet. To start off, we'll read François' bio. François is a software engineer and artificial intelligence researcher at Google. He is the creator of the Keras deep learning library released in 2015. His research focuses on computer vision, the application of machine learning to formal reasoning, abstraction, and how to achieve greater generality in artificial intelligence. His interests lie in understanding the nature of abstraction and developing algorithms capable of autonomous abstraction, democratizing the development and deployment of AI technology by making it easier to use and explaining it clearly, and leveraging technology, in particular AI, to help people gain greater agency over their circumstances and reach their full potential. He has published the popular deep learning textbook, Deep Learning with Python, which has been translated into 13 languages. Welcome, François. Thank you for taking the time. You are a very prominent figure in the space of artificial intelligence. And so to get things going, we would love to know where your interest in tech and in computer science and artificial intelligence started.
Well, I was fascinated with computers since before I had one. I was actually pressing my parents for to get one.
How come? What was fascinating about it?
I'm not sure, but yeah, as a kid, I just love computers. They were just fascinating to me. I can't really explain why, what I was seeing in them, but it's just a thing. Just how it was.
So you pressed your parents for the computer and you finally got one.
Yeah.
And what was the first thing you did with it other than
playing video games? Obviously.
Okay.
That's the modern thing. No, but I guess the next thing I did was I took up digital painting. Right. So I got a pen tablet, like an early Wacom pen tablet, and started painting. And I got I think pretty good at it for a teenager at least.
What did you paint?
At first, mostly video game fan art because, I was really into video games.
That makes sense. And you sort of started on this sort of journey of computer science and playing with computers. And so did that translate a lot in school as well? Or was that sort of your passion and interest in computers kind of was a sort of a hobby on the side? Or did that also come from school?
Definitely did not come from school. So honestly, I don't feel like I got much from school, from middle school in particular. It was not a great experience for me, to be honest. But yeah, I'm not sure where my interest in tech really comes from, to be honest. One thing I know is about age 15, 16, I decided that what I needed to do with my life was invent artificial intelligence, invent AI, true AI, and use it to make robots. And I'm not entirely sure where that idea came from. It was probably the influence of Asimov, like the robots book series. That's probably at least parts of where this came from, but I don't remember the specifics. I do remember that I had this idea, and it became my thing, right? And the first thing I started doing when I started focusing on this idea. So back then, I had no programming experience, right? I was, in fact, not very familiar with, tech in general because I was mostly into reading, drawing, writing. I was actually not doing that well at subjects like math, for instance. So the first thing I did is I started listening to neuropsychology lectures online. So this was 2005, 2006. It was the very beginning of the MIT OpenCourseWare program, which is this. It's about recording MIT lectures and open sourcing them, basically putting them online, freely available. And so I started listening to these neuropsychology 101 lectures from MIT, and it was very interesting actually. So my basically my naive assumption is, well, we probably know a lot about how brains work, right? We probably know enough to use that knowledge to start implementing AI. And well, the lectures were super interesting, but at the same time, it quickly became clear that we sure know a lot about brains, but what we have is this big collection of observations. And what's missing is an actual model of the brain, like an explanation with regard to how the brain implements thinking, or reasoning, or memory, or perception. And so that was kind of disappointing. So I came away from this experience, thinking that neuropsychology is cool and interesting, but it's also kind of useless when it comes to implementing AI.
And it was useless because what you wanted was sort of a model of the brain.
Yeah, an explanation, exactly.
Right.
An explanation rather than just, a collection of anecdotes and observations. But the lectures were great. Like it's the lecturer. I don't actually remember who the lecturer was, but very interesting, very good. So after that, I was like 17, 18. So I got busy with math and physics. I went to something called a classe préparatoire, which is like a 2-year, very intensive math and physics program. So I did that.
By choice?
By choice, yeah, absolutely by choice. Because I wanted to do science. Obviously, I was interested in AI, so I wanted to do science, and this was basically the only path available for me at the time.
Right, because you said like you weren't doing well in middle school, and
in middle school, yes, originally.
You...
It's not because I couldn't. It's really just because the teachers sucked. And the environment sucked. So by my final year of high school, I was getting top grades in everything. So I went to a classe préparatoire. I actually enjoyed it. It was an interesting time. But I was obviously extremely busy with my studies. Then I joined an engineering school, and I picked that engineering school because it had a pretty good robotics department. So I joined when I was just turning 20. And from that point, I started reading a lot of AI research papers. Also at that time, I read the book On Intelligence by Jeff Hawkins, which I really loved. It was like one of the sort of like milestones on my path. So very, very interesting, very inspiring book. Another researcher that caught my attention at the time, so when I was 20, was French researcher Pierre Voudeillet, who was an early pioneer of research on artificial curiosity, intrinsic motivation, and so on. So very, very interesting stuff. So I was really into that sort of topic. So one of the first books I bought was Artificial Intelligence: A Modern Approach by Russell and Norvig. And that was very much algorithms. This was very much applied engineering type of thing, with no power to explain anything about thinking itself. So that part was also kind of disappointing for me. Like I went from learning about neuroscience and being disappointed to learning about what was AI at the time and being very disappointed in it. But what I found to be really cool and interesting back then at the time was a tiny subfield of robotics called cognitive developmental robotics. And what was really interesting about it is that it was all about building models of how young children basically develop cognition, how they learn to learn, and so on, and trying out these models in robots. So why robots? Why not simulations, for instance? It's really because one of the core ideas of cognitive developmental robotics was that cognition was embodied. Like you need a body in order to start thinking, and this is something I truly believed as well. So when I left my engineering school, I actually started doing research at a lab that was strong in that area, which was at the University of Tokyo. So I moved to Tokyo, started doing research. And I really enjoyed it, actually.
That's an incredible journey and quite a unique one. The question I want to ask is, there's a fascination with understanding the brain and by default adding some kind of value judgment to the fact that our brain is very, very superior and wanting to then understand it, but then also wanting to replicate it. And my understanding of AI is kind of, it's wanting to replicate that intelligence in machines. Would you agree?
I guess, yeah, at a very high level, that's a dream of the field. In
Right.
practice, if you look at what people doing AI actually do, very, very few people are working on models of general intelligence, of models of the brain. It's an extremely niche research topic. So in the past, before the rise of machine learning, most people were doing algorithms. They were doing like search, planning, A-star, and so on, which has actually nothing to do with the brain.
Right.
And then later on, machine learning became a big thing. So people started doing things like random forests or gradient boosted trees, which again, decision trees have nothing to do with the brain. And then people started just fitting curves because it turned out to be a really powerful way to learn stuff. So people started training deep learning models, which are basically these very high dimensional parametric curves. Again, that's not quite how the brain works. You could say that's how maybe a subset of the brain works. That's like the perception subsystem. If you tell me, hey, perception in the brain is probably implemented with some rough biological equivalent of gradient descent, I think that's plausible. But that's just perception. Most learning in the brain is not gradient descent. Is not curve fitting. So I really think very, very few people are actually trying to even ask the question, what is intelligence, and what would be a good model for it, or even a good definition for it. Most people like when people say, for instance, they're working on AGI. Typically, what they mean is that they're working on scaling up LLMs. LLMs are definitely not a model of the brain.
Right. Large language models.
Yeah, that's right. Yeah.
My understanding is sort of to reproduce this concept of intelligence, but you're right. In practice, it's evolved in a very, very different way, and the outcomes have also been very different. And so, just coming back to your story, was that what was driving you to go into the field? This concept of wanting to mimic intelligence in sort of machines?
Absolutely. Yeah. The very first question I started asking was actually not so much how can I recreate intelligence, but just I just wanted to better understand intelligence in humans. Like, how do I think? Why am I conscious? How does any of this work? Right? I do believe that trying to model it, recreate it, so not just like come up with a theoretical model, but come up with an algorithm and implement it and try to run it in practice is basically the only practical way of making progress. I think if you just like sit down, read papers and think very hard about AI, which is basically what I was doing at between 15 and 20, you're not going to get very far. Like at 20, I actually came up with my first model of general intelligence, and I think it was pretty clever. It got a lot of things directionally right, but because it was still at this stage where you just think about things and write them down, it was very much ineffective. Like, in order to make progress, you really need to come up with something that's algorithm level. You need to implement it. AI is very much applied engineering, and to make progress in AI, you need to get into that feedback loop where you can implement something, run an experiment, see the results, and use that to inform the next iteration.
So does working in sort of the field of machine learning help you understand the brain? And then there's sort of this feedback loop of the more you understand about the brain, the more you can feed it into sort of artificial intelligence. And then the more you learn about artificial intelligence, it teaches us about sort of our own learning. Because the underlying question to that is if you were so interested in the brain, why not go in the medical?
Why not go into neuroscience? Exactly.
Right, yeah.
Well, I thought about it, but ultimately, as I told you, I found neuropsychology to not be a practically effective way to understand the brain. And I still believe so today. I believe that a true plausible model of cognition is not going to come from neuropsychology. And the reason why is just because to understand something, it's not enough to observe it, to collect observations, even very granular observations about it. In order to understand anything, you need to start from a model of it. So, for instance, deep learning emerged very much because it was getting good results on perception problems, right? That's how it got started. That's where the first successes were.
Perception means what?
Perception. So, for instance, image classification. You have a bunch of images. And some of them are dogs, some of them are cats. You want to know which ones are dogs, which ones are cats. And as it turns out, the sort of system you end up with was able to inform models of the visual cortex. And it's a little bit full cycle, actually, because the earliest machine learning models that try to solve the perception problem. So, for instance, the deep learning architecture that was very successful in that particular problem was the ConvNet architecture, which actually derives from, well, multiple things. But, for instance, deep ConvNets are partly inspired by the HMax model of the visual cortex, which was from like the 2000s. And before that, there was the neocognitron. Well, these are actually inspired by the visual cortex, right? So our study of the visual cortex kind of helped us come up with this sort of like practical algorithm for solving perception problems. And that model, in turn, helps us understand how the visual cortex actually works.
Oh, wow. Okay. So it does go back to this concept of the visual cortex informed how to sort of build these models.
At first. And
at first.
Not really in the sense that, so it's sort of counterintuitive. You might think it's like, hey, we started by understanding the visual cortex. Then we used that understanding to create a model of it, which turned out to be really powerful for classifying images.
Right.
It's actually not really that. We started with like loose observations about the structure of the visual cortex. We use that as inspiration to come up with techniques that were largely not grounded in the visual cortex, that were very much independent. We are very much guided by what is working out in practice on that image classification problem. And that algorithm eventually can be able to inform neuropsychology research.
So many things are making sense. Thank you very much for that explanation. When I come back to sort of the original question of, why not go into, neuroscience, why sort of go into machine learning? Instead of studying the sort of the theory and the observations, it's like you're building and studying a brain kind of at the same time. So you're you're feeding information from like the way that our brain is shaped to sort of inspire. But I think what sounds to me like is the joy that you have is sort of being able to build and tweak and change and really sort of get your hands on like a brain in a sense and see the outcomes of it. As opposed to,
And fundamentally, so to start with, I think it's just more fun to actually invent something, implement it, and try to run it in practice compared to just like observing biological system.
You can't really cut open a person's brain either and
that's right. And I also really believe this is how you make faster progress, right? Because you can get to this very fast feedback loop where you get an idea, implement it in practice, test it, collect the data about your idea, and then use that to inform the next idea.
Makes a lot of sense. Great. Thank you so much for sharing. So we sort of took a bit of a detour. So last time we left on your journey, you were in Japan studying a PhD program.
Yeah.
So what was that about?
So I was doing cognitive developmental robotics, and I was particularly interested in unsupervised video data processing. So you get like a video feed, and you want to be able to segment it into scenes or situations. You want to be able to build a perceptual model of what's going on in the scene and so on. So it was technically doing deep learning, but not deep learning with gradient descent. It's actually something that people may not necessarily realize, but you can do deep learning without gradient descent, just like layer-wise. And so what I was doing was basically building a modular hierarchical representations of a video feed in a completely unsupervised way, and that was based on matrix factorization rather than gradient descent, which works well enough for shallow networks. And I was able to use that to perform basically few shot video segmentation. So the segmentation part worked actually really well, and a few shot classification or clustering. So basically, it's like, hey, if you see like a specific hand gesture, then you see different hand gesture, and then you see the first hand gesture again, you can tell it's the same one as the first one. So you're simultaneously able to tell where the gesture ends and begins and ends, and you can cluster them basically. So that was what the research was about. So that was fun, but then I needed to actually make money. So I went into the tech industry. I did a couple startups.
Wait. You founded startups?
No, I joined.
You joined. Okay.
Joined a startup.
Okay.
And then I joined another startup. But I was so I moved to first New York City, then San Francisco, and I was very much trying to do my own startup. For like visa reasons, I was not really able to start a company at that time. So at 25 I started Keras, and after that I joined Google, and I actually ended up working on Keras at Google, and that's what I've been doing since.
Okay, so Keras is a big part of your life.
It is.
What is Keras?
So Keras is a deep learning library in Python. It works with TensorFlow, of course. It also works with PyTorch and JAX. And it's basically this Python-based toolkit that enables you to very quickly build any kind of deep learning model you may need and train it on your data.
So how did this idea come about? What was sort of because I'm sure you didn't just wake up one day and be like, hey, I'm gonna build a deep learning library. Like this must have been a process.
Definitely not. So I was aware of deep learning basically from 2009. I took note. So in 2012, the ImageNet image classification competition was won by Gusatvo and Gusatvo with a deep convnet trained on GPU, which was not the first time that someone had won an image classification competition with a deep convnet trained on GPU. There was Dan Searson before, a year before. But my lab at University of Tokyo actually ended up second. And you've never heard of their entry because they were second, they were not first. But because they were second, I was like really curious about this first place entry. So I took note that like deep learning is clearly a thing. This is going somewhere. Then I got busy with the startup stuff. But I kept working on or learning about deep learning in my free time. And one thing I was especially interested in were recurrent neural networks, which were like at the time the interest in recurrent neural networks was like very, very early. When I launched Keras, the deep learning community was like tiny. It was like maybe 10,000 people. So in early 2014, so back when deep learning was this very, very niche academic topic, I started building a question answering engine. It was called quickanswers.io. And it was basically a text box where you could ask a question and get an answer. And the tagline was, ask any question and get a short, to-the-point answer snippet. So I launched that, and it got a decent amount of traction, actually. Like, it was apparently interesting to a bunch of people. It was like, a 2014 version of something like ChatGPT or Gemini, in a way. And what it was actually doing is it was doing an early version of what is now known as RAG, retrieval augmented generation. So what it was actually doing is you would type in your question. It would normalize your question into a sort of standard representation. It would run a Google search query with it. And from the results, it would extract a bunch of relevant text snippets. And then it would run an LSTM text generation model to sort of like try to summarize those text snippets into a relevant answer. So it was retrieval augmented generation, but like long before that was a thing. So in 2014, got quite a bit of traction. And in the process of building this thing, which by the way, so it worked decently well. Actually, if you look up like my Twitter feed from that time, you'll find a bunch of examples of this thing in action. It worked decently well, but the technology just wasn't there at the time. And in the process of building this, I got really into LSTM models. So LSTM is like a type of recurrent neural network. And at the time, there was like no open source software for building RNNs or LSTM models, like at all, whatever. And so I was like, I need something, so I'm just going to build my own. I started building something on top of the deep learning framework Theano, which was like kind of an ancestor of TensorFlow in many ways. It was roughly the same architecture ideas as TensorFlow, except it was maybe not as professional. It was done by like an academic lab. And so in early 2015, I decided, I've built this thing. I'm just going to open source it now. And so March 2015, I launched it. I picked the name Keras. And it very quickly got traction. So the deep learning community was very small. And because it was so small and there were so few people doing it, everyone basically took notes of it. And the timing was right as well, because the interest in RNNs really started picking up steam. And the easiest and best way to do RNNs back then was just Keras, right? So lots of people started adopting Keras. I joined Google because I thought it was a nice opportunity, and I really admired Google as a company. I was a big Google fanboy basically back then. In some ways, I still am. Like about 6 months later, Google actually released TensorFlow. And I was like, well, TensorFlow is clearly the future, so I should rebase Keras on top of TensorFlow. So I did that. So it was multi-backend. It could support Theano or TensorFlow. And a year later, the head of TensorFlow, they noticed that, half of TensorFlow users externally are just using it through Keras. Keras seems to be a big thing. It's growing fast. So he came to see me and was like, hey, why don't you join the team? So I was like, yeah, sounds good. I like working on Keras, so I would enjoy, working full-time on it. Before that was actually not my full-time job. So my full-time job was actually doing computer vision research for Google Photos. So I stopped doing that. I just started doing Keras full-time. I've been doing Keras full-time since, with some research on the side. Yeah, that's basically the Keras story.
I learned so much just by listening to all of this. And as a Keras user, that's great. I didn't know all the story behind it. How did you get to Keras 3? What was your take? How much work was in it? How was it?
Sure. So Keras 3, maybe we can start with like what's Keras 3 exactly. Keras 3 is like a complete rewrite of Keras that makes it multi-backend again. So for some time, Keras became TensorFlow only, because before Keras was like TensorFlow and Theano, and CNTK, which was yet another niche machine learning framework. But CNTK kind of died out, Theano died out. There was just TensorFlow. So for a while, Keras was TensorFlow only. But today we are actually in a multi-framework world. Like TensorFlow is very popular, but PyTorch is very popular as well. JAX is also very popular in the GenAI space. Like many of the top GenAI players are using JAX, like Cohere, Anthropic, Midjourney, and so on. Midjourney is actually also using Keras 3, by the way. And so I really wanted Keras users to be able to benefit from all of the ML ecosystem had to offer, not just a subset of it, which would be the TensorFlow subset. I kind of settled on the idea at the end of March last year. Started coding basically in the last days of March, early days of April. The first prototype was done by May. Then we did like quite a bit of internal alpha testing. And early July, we actually released the package as Keras core. And this was a big team effort. So I wrote maybe like 50%-ish of the code, but it was a big team effort. Like everyone on the Keras team worked on this thing. So we released Keras core, which was basically the public beta, and the final version was released like 3 months later. So now like Keras 3 is generally available, so it's like stable, it's production ready. It's already used in production by a bunch of companies, including Midjourney, which is a pretty nice anecdote. And so what's really nice about Keras 3 is that you can really write code that's backend agnostic, meaning that you can pick which framework you want that code to execute with. So you can pick TensorFlow, you can pick PyTorch, you can pick JAX. And what's really powerful about this is that it makes sure, ensures that you always get the best performance for your model, because you can switch backend based on which backend is going to be the fastest for your particular model architecture and your particular hardware. And a lot of the time it turns out to be JAX. JAX is the fastest. Sometimes for some models it could be TensorFlow. For some models it could be PyTorch, right? And you're basically sure that you're always going to be like 20 to 30% faster than if you were just stuck to one backend. Another really nice thing is that you can start benefiting from the entire ML ecosystem. Like if you have a Keras model, it's a Keras 3 model, it's multi-backend, you can use it with packages from the TensorFlow ecosystem, like TFJS, TFLite, and so on. You can use it with packages from the PyTorch ecosystem as well. You can even use it with packages from the JAX ecosystem. And the thing is, you don't even need to be a Keras user. Like if you have a Keras 3 model and all your workflow is like low-level JAX code or low-level PyTorch code, you can start using the Keras model as if it were a JAX function, as if it were a PyTorch module. You don't even need to care that's a Keras model, right? And this also makes it really powerful if you want to release an open source model. Like, PyTorch is about half of the market, TensorFlow is about half of the market. JAX is much, much smaller. And well, if you release a model and it's like only PyTorch or only TensorFlow, then it's usable by half the market, right? If you release a Keras 3 model, then anyone can use it, like regardless of their framework of choice, even if they're not a Keras user.
Agree. I think this changes a lot because I've been in this field for a while, and there's always this, oh, did you see this model? No, I can choose because it's in the other framework. No matter which you are, there's the other framework. And then there's the research that sometimes, hey, you're doing this research, I'm doing similar, but with different frameworks because we are experts in different things. I guess the idea that having, how about we all work on this Keras thing, and we can all share better and collaborate and move faster, I would say. So this, first of all, this is a great idea. And the community like very much. I've seen the repository. There's lots of commits from the community, right? People are very excited. How did you see that? First of all, when you first did it, how did you think would the community react? And how did you see them reacting after the release?
All right. So Keras is really an open source, very community-centric project. So we get lots of community contributions. We love our community. So you're always welcome to contribute, and we will help you make your contribution the best possible. When I launched Keras originally, I had no idea how people will react to it. It was just like, hey, I made this thing, I might as well open source it, type of thing. And well, in the following years, I kind of learned how to manage an open source community, which is, by the way, it's really something you have to learn. I don't think you can really improvise it. But now I've been doing this for like 9 years almost. I got decent at it. I've got a lot of practice. And I think open source is great because, well, not only the software you're making can have the most impact because it's really usable, it's very available to anyone, but you're also helping other people who are trying to learn, who are trying to make progress on their journey. Like they try to contribute, and you kind of sort of like guide them towards industry best practices. You also help them, build up credentials because they can say, hey, I implemented this feature in Keras, which is always nice on your resume, right? So it's a nice way to give back.
I guess one thing that I've noticed from some of my friends that work on this is, hey, Francois left some comments on my commit, and they're very excited about, oh my God, I did this, and Francois, he left a comment, and it's like they are people like Sayak, for example. I guess Sayak Paul, he commented many stuff, and they are. It's fun because you talk to them, you see their eyes shining. It's like, oh my God, that's so cool. And that's exactly as you said. You have to you cannot wing it, right? You have to learn how to deal with the community the best way possible. I guess that's why it's so successful.
And I'll just say that it's so nice that you're so still involved with it. After 9 years, it could be easy to say, okay, I built this, putting it aside, I'll move on to something else. But you're very much like you live and breathe it, and you're really dedicated to the community as well.
I'm still coding. I'm still reviewing the PRs. I'm still leaving feedback on PRs and so on. Yeah, it's still very much my day job.
It's great. And I have 2 questions still on the topic. First of all, the main question that people might be asking is, when is the new book coming? Because
right,
I'll tell you something. I read both of them. They're beautiful. First of all, they're beautiful in terms of colorful and stuff, and beautiful in terms of you. For example, they are a book that, let's talk about RNNs here, CNNs in this chapter, and so on and so forth. So technically, you could maybe jump chapters, right? I want to learn about this topic specifically. I'll jump. That your book is more than just, this is how to use Keras. Nobody needs that. It's different. No, because you can learn that in the documentation, right?
That's right. You can just read the docs. Right. Yeah. So totally. So what the book is trying to do is not just like describe, here's how you do this. It's trying to help you build intuitive mental models and actionable mental models about how things work. And as you say, you can actually read it cover to cover because it's trying to sort of like tell a story. It's not like each chapter is independent. Like each chapter is going to be building aspects of your intuition that actually they're building upon previous aspects that you learned in the previous chapters. And so we are trying to sort of like incrementally build up this mental model of deep learning and AI and Keras and all these other things. I'm also trying the best I can to make it sort of like feel like a story, like try to be context rich, like insert notes about some historical facts, not just talk about here's how like LSTM works, but talk about here's how LSTMs were actually developed, like here's what the authors were actually thinking about when they invented it and so on. I think that's helpful.
No, that's beautiful. Please continue doing that. But you didn't give me a date.
Right. So I'm currently working on it. It's definitely not really close to ready. My best guess is probably like mid 2024 is when it's going to be out.
That's amazing. Perfect.
Yeah, it's a little bit late on schedule, but
that's great. So we have this beautiful release that happened with the Gemma models, and they have a very beautiful integration with Keras. I'm so proud to be able to collaborate on this because this was part of when I saw the model for the first time, I said, we cannot launch this if it's not available in Keras at the same time. That's when people will take advantage of. That's when they will use it. That's giving a good user experience. And I'm very glad that we could make it happen. I'd like to take to hear your perspective on that.
Right. So the Gemma model is a new open source LLM by Google. It's as far as benchmarks go, it should be the best available on the market. And in my opinion, one of the best features, by the way, since we are talking about benchmarks, is that Google has really this state-of-the-art test set filtering mechanism. So you're quite sure that the benchmark numbers that we are putting out overfitting do not reflect training on a test set, which may not necessarily be the case for other LLMs available. And so we've made a Keras 3 implementation of Gemma. And so of course it's Keras 3, so it's multi-backend. You can run it with JAX. It's typically faster with JAX. You can run it with TensorFlow, you can run it with PyTorch. I'm really excited about it. I think the code looks beautiful. The model is really good. And we've also made it, as useful as possible. So you can do a bunch of things with it. It's ready for model parallel distributed training, for instance. If you want to train from scratch or fine-tune your own Gemma, you can actually do it on like a cluster of GPUs, for instance, or on a TPU pod very, very easily in just a few lines of code. You can also do LoRa fine-tuning. So LoRa is like low rank adaptation. It's like a very memory and compute efficient way to fine-tune an LLM. And so we have a built-in LoRa API. We're making it really easy to enable LoRa on the Gemma model, or really, any other LLM from the Keras NLP package. We're also making it easy to just save the LoRa weight delta, because these models are actually very, very large. Like the small model, the 2B model, it's like 8 gigs. That's pretty sizable. So if you're fine-tuning it, maybe you don't actually want to save the entire 8 gig weights file. Maybe you just want to save your LoRa delta, which is actually on the order of like tens of megabytes. So much smaller. And then you can reload that. And typically when you reload, you won't even have to re-download the original checkpoint, because it's probably going to be cached locally in your image, right? So we're really excited about that. We think this is like one of the best features of Keras NLP. So yeah, try that.
Definitely. I really want to keep talking about large language models, but before that, I would like to also talk a little bit about the Keras and Kaggle integration.
Yeah.
Which is also something that highlights how we are empowering like a gigantic community. The Kaggle community is enormous, and bringing one thing that I've been working with your team is bringing Keras starter notebooks to the competition, something that you did yourself. Of course, you did way better than us, but we keep doing so people can, because starting a competition is hard, right? It's not like trivial. It's let me do stuff here. No, it's not like that. So what the idea was, we give you a starter notebook using explaining how Keras work, and people can learn two things. They can, Keras, cool, nice, and the competition data, cool, nice. I get something. So they get two things for the same notebook. And this is another thing that we've been working. What's your take on that?
Right. So Kaggle is this machine learning competition website, and also, I think it plays a role as a sort of like machine learning social network almost. Like it's very much a community of users. It's a very large community. It's like 12 million users. Like by comparison, Keras is like 2.5 million users. And yeah, no, I love Kaggle. Like first of all, like let me state, I love Kaggle. I've been a Kaggle user since 2013. I actually won my first Kaggle competition in 2013. It was a text classification competition.
Wow.
Then 2013, 2014, 2015, I was very active on Kaggle. In 2015, I actually made a bunch of like Keras notebooks, like very early Keras notebooks. And this is actually something that we are still doing to this day. Like we are releasing, as you mentioned, these competition starter kits using Keras, and the community really loves them, because it gives you a starting point. Like you don't have to start from scratch. You can just fork this thing, customize it, make it your own. And so you mentioned this Keras and Kaggle integration. So what's going on is that Kaggle has launched Kaggle models, which is basically sort of like model hub or model database for pre-trained models of all kinds in any framework you can imagine. And all models from the Keras CV and Keras NLP packages are on Kaggle. And so that means two things. So one is that you can start using these pre-trained models in an offline notebook. Like, in Kaggle competitions, many competitions are in offline mode, which means that you would enter them by submitting a notebook, and the notebook will run on the private test data for the competition with no internet access. And there's no internet access to avoid leaking out the test data, obviously, which would be problematic. Well, now you can actually use all these Keras CV, Keras NLP models in offline mode. And beyond that, people from the community can start uploading their own fine-tuned versions of these models to Kaggle. And then anyone on Kaggle can start using these fine-tuned versions. So it's like sort of like model sharing platform. So we are really excited about that.
I agree. That's as you said, community, right? Communities, when people can share back and forth, and that's what pushes us forward.
Yeah.
And I guess it's an interesting point in terms of the sharing, and we talk a little bit about Gemma and the large language models. And last year and the year before was kind of if you've been doing machine learning for a long time, I imagine you didn't see like a year like 2022 and 2023 in terms of things happening so fast, and not necessarily good things, but a lot of hype. That's like, I guess I like reading your Twitter feed because you have some very strong takes on some opinions that like, I don't know why they had like some very weird opinions, and you come and say, no, that doesn't make any sense. So how do you see this? First of all, this hype around AI that started in from someone that's in the field for a long time. You saw robotics, how the pace they evolve. You saw neuroscience, how the pace they evolve. All of a sudden, AI became like insane. Everything is happening. How do you see that going on?
Yeah, so there's definitely a lot of hype around LLMs, and I mean they're clearly badly.
Wait, LLMs or AI?
Both, but the thing is, like lately, people have been kind of equating the two. Like people, when
Okay.
people say AI, what they really mean typically is LLMs. And well, there's a ton of hype, right, which is not really justified, and people are extrapolating things that, as you say, don't actually make any sense. But at the same time, that doesn't mean that LLMs are useless or like they're fad. They're very much not fad. They're actually a very big development, and they're very useful. But when people say, LLMs are a prelude to AGI, artificial general intelligence, to like human level intelligence, well, that's definitely not what they are. So LLMs, they're transformers, they're deep learning models. So like we were mentioning previously, like deep learning models being big curves that's fitted to a training data set. This is still what LLMs are. They're like entirely based on curve fitting. They're entirely based on memorization. And well, as a result, they suffer from a number of problems. They're prone to hallucinations. They're very patchy generalization. They're also, it's very hard for LLMs to deviate from exact patterns that they've memorized, right? Like one example, is if you prompt an LLM with some modified version of the Monty Hall problem. I don't know if you're familiar with the Monty Hall problem.
No, I don't.
It's like, okay, so let's talk about this then. So it's this. You can picture a game show, a TV game show, where you have 3 doors, and behind one door there's a car, and you want to get the car, and behind the other 2 doors there's a goat, and the TV show host, so named Monty Hall, will so let you make a choice, and you pick like some door, like let's say you pick door A, and then the host is gonna open one of the other 2 doors, right? And it will show, oh, there's a goat there. Hey, do you want to change your choice or keep your original choice? Like, do you want to switch to door A, or do you want to keep switch to door B, or do you want to keep door A? And well, it's actually very interesting probability problem. And the correct answer to this problem is you actually get a higher chance of winning by switching your choice, which is somewhat counterintuitive for many people. But roughly the reason why you actually get a better chance by switching your choice is because when Monty Hall decides to open a door, they know what's behind the door. And the specific door that they pick, that's informed by that knowledge. And that action is actually providing some extra information about where the car might actually be, which is why now the door that was actually not opened, but was also not your original door, actually ends up with a higher chance of having the car behind. And anyway, if you prompt an LLM, so this Monty Hall problem description is something that an LLM has been trained on. It has seen, in fact, hundreds of instances of this problem with different variants and everything. So if you prompt an LLM with a modified version of the Monty Hall problem, where you say, hey, there's 3 doors, I pick door A, and then Monty Hall opens door A, and you see there's a car right there. And Monty Hall asks you, hey, do you want to switch your choice, or do you keep door A, where again, there's the car. If you prompt the LLM with this version, it will actually tell you, yes, I should switch choice. And the reason why is because it doesn't actually understand the text that it's reading. It's repeating something it has memorized. And in this case, because it has strongly memorized the answer of the actual Monty Hall problem, this is what it goes with.
Which is that you should choose a choice. That
which
choice
you should
is better.
change. Yeah,
right.
you should change choice, because that's the official answer of the actual problem.
Right.
And Well, there's actually one way to patch this issue, which is to patch it for this specific scenario by retraining the LLM on modified scenarios of the multi-role problem. But then the thing is that you have to repeat this sort of like one-time patch for every other problem. And the only way to patch that is to actually retrain the LLM via RLHF specifically on this problem. So they cannot really deviate from patterns that they've memorized. And they're very, very patchy generalization. And they cannot handle any sort of like task or scenario that they're not familiar with, that they've not been trained on. So the way I think about LLMs is LLMs are basically, so they are stores of knowledge, information, but they're also stores of programs. They've seen sort of like every pattern you could see on the internet, and they've stored them in the form of vector programs. And they can even interpolate between different programs. And when you query an LLM, what you're actually doing is that you're retrieving a program from this latent program space and running it on your data. Like for instance, if you ask, write a poem in the style of Baudelaire or something, well, write a poem in the style of is like a program that's somewhere out there in the latent space. And it's an interpolative program, by the way, which is why if you change the formulation of the prompt a little bit, you will get a similar close point in program space. It's not exactly the same, which, by the way, is the origin of prompt engineering. Like your first question formulation is probably not the best program coordinate for what you're trying to do. And so if you want to find the best program coordinate, you have to search a little bit of a program space, right? That's what prompt engineering is. And well, this is all extremely useful, like being able to store these like millions of potentially useful programs, being able to reply them, being able to interpolate between them. This is tremendously useful. You can use that to automate or enhance many different tasks across any number of industries. But this is not the way intelligence works. Like humans are not just sponges of data and programs that are completely unable to deviate from what they've memorized. Humans actually have general intelligence, and general intelligence is very much the ability to adapt, the ability to make sense to situations you've not been through before, right? So I don't know if you know Jean Piaget. It's like the father of developmental psychology, and he had
He's
actually
got the 7 stages.
Yeah, exactly. That's what he's really known for, like the stages of cognitive development. And he had a very well phrased, I think, quote about this. He said, intelligence is what you use when you don't know what to do. It's what you use when you're experiencing something that you've not been prepared for, right? So like your past experience has not prepared you for this moment. The prior knowledge that you're born with, like inherited through evolution, basically, has also not prepared you for this moment. And so that's when you have to use intelligence. And LLMs have basically no intelligence. What they have is memorization. And as long as you're operating within their training data distribution, so meaning that you're trying to solve a task which has a solution which has been memorized by the LLM in its training data, then the LLM can do it. All you have to do is find the right prompt, which is the right program coordinate in this sort of like program space, a sea of different programs, vector programs. So you find that prompt, and now you have automated the task. You can just reapply the program on your data. What they cannot do is synthesize new programs on the fly to adapt to something they've not seen before. They basically, and this is, by the way, this is independent of task complexity. If you ask an LLM to do something that they're not familiar with, even if it's a really, really trivial problem, they're not going to be able to do it. And you see this, for instance, on the ARC challenge. So the ARC challenge is sort of like IQ test for machines that are released in 2019. So before the rise of LLMs, right? I was releasing this as a way to test and illustrate my definition of intelligence. And my definition of intelligence is basically, it's exactly what I just told you, that intelligence is about the ability to adapt, which basically means it's about the ability to efficiently acquire new skills at tasks that you were not prepared for, right? That you were not explicitly trained to do. So how efficiently can you pick up a new skill? Well, in the case of LLMs, it turns out the only way you can get them to pick up new skills is by fine-tuning. And fine-tuning, as it turns out, is tremendously inefficient. So LLMs are not very intelligent. I would say they have non-zero intelligence. And this is actually reflected in the fact that they score non-zero on the ARC test, but they have very, very, very low intelligence. And so ARC is pretty interesting because it's a set of like few shots, sort of like puzzles, kind of IQ test like. And well, any human can solve like, well over 80% of these puzzles. And meanwhile, for AI systems and deep learning models and LLMs in particular, it's completely out of reach. Like the state of the art today is 31%, which is not based on LLMs. And if you take an LLM like Gemini or ChatGPT-4 and you just prompt it to solve these puzzles, it will score like between 5 and 10% typically. And none of these puzzles is really difficult. Like you can give them to a 5-year-old and they will do a great job actually. And the reason why is because the 5-year-old actually has general intelligence. They can see something they've never seen before and make sense of it, right? And each puzzle is novel to some extent. Like it's probably not similar to anything you could see on the internet. But anyway, yeah, this is really interesting. It's like these are very, very simple pattern-based reasoning puzzles. LLMs can absolutely not solve them. They cannot solve them because there's no direct match between these puzzles and something they've memorized. But the 5-year-old can actually solve them because they have intelligence, because they can adapt, right?
Do you think that the transformers architecture, which is the base of most of it, it might not be the solution, might be in a local maxima, let's say like that, for the AGI search, let's say like that?
Yeah, so I mean, transformers have been tremendously successful. And I don't think there's zero overlap between transformers and the brain. If you look closely at what transformers actually do and why they work, I think there's an analogy between learning in transformers and Hebbian learning in the brain. And the base of the analogy is that transformers, via the self-attention mechanism, they have this ability to embed together, like spatially together, concepts, things, which in the case of a transformer, it's like tokens. So embed together tokens that are semantically similar, which is basically a proxy. So one proxy you can use for semantic similarities when they co-occur together. And the way self-attention achieves this is because in self-attention, you're going to be looking at token embeddings. You're going to be computing a dot product between them. And that gives you a similarity score between these 2 points. And self-attention will have this tendency to pull closer together token embeddings that already have a higher dot product. And so this basically implements Hebbian learning very much. And I do believe that there is a decent analogy between that sort of learning and what happens in human sort of like passive perception. Everything that you learn passively, like if you look at young kids learning, well, it's pretty clear that they do some amount of this sort of like passive, unsupervised learning, like predicting the next sensory motor frame type of thing, which is basically what transformers are doing. But most learning in humans is not that, right? It's not passive. I'm gonna learn the next sensory motor frame. It's actually active learning. It's much higher level learning. It's causal learning, and
it's like let me try this and figure out.
Exactly. It's like you learn via play. You learn actively by actually experimenting, by trying things out, seeing what happens, and then learning from it, and using that learning to inform the next experiment. Just like you would do as a scientist, actually. Like young children are actually behaving exactly like scientists, and they're just doing it like intuitively. And I mean, you see this especially, for instance, in the way kids learn language, right? Like a 2-year-old doesn't learn to speak by predicting the next token, like passively based on what they've heard. That's not what happens. For a 2-year-old, language is first and foremost, it's an action. It's an act. Like they're using words as a way to influence their surroundings. like the same way you would use your hands and your arms to reach things. It's a way to reach things. That's what language is. And kids, you can tell they're not just learning the next token because they only arrive at grammatical correctness very, very late. They start out with the important bits of a sentence in place, like subject, object type of thing, and everything else is missing. So they get the sort of like zoomed out macro structure right long before they actually get the next token thing. They are using language, they're interacting with language again as a sort of like motor modality, the same way you would use your hands, for instance.
I wanted to come back to this concept of hype has come from it also reaching sort of mainstream too. And so your answer explains that we're really far, very, very far from AGI, and that ultimately LLMs and the current state of AI and machine learning is very much in a beginner stage. So it doesn't sound like you're very worried about the future.
No, I'm not. I know there's a lot of talk of existential risk created by AI. I'm definitely not worried about that, at least, based on current technology. Like LLMs are not going to magically morph into autonomous agents with superhuman capabilities. LLMs, again, they're like big curves fitted on human-generated data. They're very much limited to that training data. They can only operate within their training data distribution. So there's no real need to like build a prison around this type of AI because it's already in a prison. It's imprisoned by the latent manifold. No, I'm not worried about existential risk for sure. I mean, that's like pure science fiction. That said, I do believe there may be some concerns around the deployment of AI at scale. For sure, like its impact on culture. Maybe as well its impact on employment. Like I don't believe AI is going to cause mass unemployment, but it will definitely affect specific jobs. In aggregate, the employment market will be fine, but some professions will be affected for sure.
Of course, I don't see it as an existential threat the same. Of course, LLMs are very useful, but I guess the hype that was created around them make them seem like almost magical, and it's not like it. It's like it's a super fancy autocomplete with a lot of work, but it's as was said, it's still has its flaws.
Yeah, I'm not a huge fan of the autocomplete metaphor because so we all have already a mental model for what autocomplete is because it's on our phones. But I don't think that's really the mental model that's right to think about LLMs. I think probably the best mental model is you can think of it. You can think of an LLM as a database of programs, and of course, it's not the kind of programs that you're used to in like Python and everything. They're vector programs, and they're actually continuous. You can actually interpolate between them. But it's very much like a database of memorized programs. I think that's actually the more constructive, the more explanatory mental model for LLMs. And well, that's tremendously useful. You can build a ton of really useful applications on top of that. But that is not intelligence, right? That is not autonomy. That is not reasoning. That's in fact not very much. That is just memorization. Well, memorization is tremendously useful, but again, it's not some kind of magical free lunch that will give rise to superhuman autonomous AIs. And really, if you're talking about human level AI and what it would take to get there, we are very, very far from it. As I mentioned, I see intelligence as the efficiency with which you can pick up new skills, and LLMs would score non-zero but extremely, extremely low on that scale, right? And in general, we are making baby steps along the lines of being able to do few shot learning, being able to like synthesize new programs to adapt to novel situations on the fly. We are very, very far from anything that would be human level. Doesn't mean that we are not going to get there in the foreseeable future. We will eventually get there. It's very hard to tell, when exactly and what form this will take. But we are not getting there, next year or in 2 years. That's very, very implausible. And when we do get there, well, LLMs may be part of the solution, but they're not going to be the most essential part. In the same way that I don't think like the visual cortex or the auditory cortex, they are not like the most essential thing about the way human intelligence works.
Thank you so much for being with us today and for taking the time. This was a fascinating conversation, and you shared so much, and we're very, very grateful for this. So thank you.
Yeah, thank you for having me.
If you would like to learn more about our conversation or our guests, check out the links below. Please subscribe, and if you're feeling extra generous, give us a 5-star rating. We would love to hear from you, so leave us a comment. We'll read every one. Until next time, thank you for listening.